Hey there, students. So I wanted to talk today about the law of cosines. We just covered the law of sines. We have practice, and generally people are feeling pretty good and ready with the law of sines. But for the law of sines, since we have like sine of A over A equals sine of B over B equals sine of C over C, we need like C and C or A and A. We need those pieces that are opposite each other in order to use the law of sines. So the law of cosines will answer the question, what if we didn't have pieces that were across from each other? So let's say we have this triangle, and I'm going to go through it. This is like a proof of the law of cosines is what I'm going to go through first. So this is where it comes from. So if we have this triangle and we know we've got A, B, C, we know how to label these sides as well. This would be, that's much bigger. This would be side A is across from angle A, and this would be side B, which is why we need those pieces across from each other in order to use the law of sines. Great, so we've got angles and sides all marked. Then in order to use our trig ideas, other than the law of sines, the only other thing we know so far is those basic trig ratios, which means we need 90-degree triangles. And we saw that we can drop this altitude or height in there. And that height then is 90 degrees here. And I'll call it H for height, because I've already used A, so I don't want A for altitude. That H isn't very clear. Let me just do this. H for height. Great. So those are all pieces of the triangle. And I'd also like to note that C is the entire side here. But in order to think about these triangles today, I need to label these bottom pieces. So I'll kind of color code this. I'm going to call this side over here. Oh, and it's not going to go on top. That's lame. I'll put it, oh, there we go. That's a piece there. I'm going to call X. And so if C is the entire side and X is this piece over here, then the other chunk over here, like, I guess, let me make it clear. If I label that point P, then I could look and say segment AB minus segment AP is segment PB. That's what we have left here. It's just the whole piece minus that chunk. So AB, that whole piece, is C minus AP is this chunk over here. That's X. So I'll keep my color coding. That's where we've got X. And I'm doing that because we don't really like X or H. We would like to get down to the sides and angles in this triangle. And those sides are A, B, and C, small a, small b, and small c. And the angles are big A, big B, and big C. So I want to get down to just those. I would like to get rid of X. That's why I'm keeping it in purple. So great. Here's our next step. We know things about these triangles. Last time we used the law of sines in order to look at stuff, or we used, like sine of A and sine of B. But another thing that we know is the Pythagorean theorem. So I'll look at triangle APC first. In this triangle over here, I could have A squared plus B squared equals C squared, which is in our case, H squared plus, I'll keep this, X squared equals B squared. Great. And just because I know where we're going with this, I'm going to solve this for H. So I'm going to say H squared equals B squared minus X squared. You wouldn't necessarily know why I'm doing that yet, but I do. So just trust me and follow me with it. Then that was the left triangle, ACP. In triangle CBP or BCP, either however you want to label it. In that triangle over there, then I'd have H squared plus this side squared equals A squared. So now I've got H squared plus this side is C minus X. So C minus X squared equals A squared. That's our hypotenuse in the right-hand triangle. And then again, I'm going to solve for H. You probably have an idea where or why I was doing this. And also, that's why I didn't solve all the way for H, because H squared and H squared are also equal. So I'll be able to set these other sides equal to each other. Well, this is A squared minus this other thing if I subtract it to this side. So I've got C minus X squared. I also know that I want to multiply this out, so I'm going to go ahead and do that. I'll use my color coding again to say this is c minus x squared. I'm a big fan of area models, so I'm going to draw that area model, but any way you multiply it out is fine with me. There's c and minus x, c and minus x, and this is c squared minus cx minus cx, and this here is negative x times negative x is positive x squared. So this equation here then is now h squared equals a squared minus the things that are inside here, which is c squared minus 2cx, because there's two of those, and then plus x squared. And good. Next, I'm going to go ahead and distribute this negative. So just simplifying this equation all the way, because I know where we're going with it. And when I simplify, I have h squared equals a squared, and then minus c squared, minus negative 2cx is positive 2cx, and then minus x squared is minus x squared. Great. Next step I'm going to go to is that h squared here, maybe purple is bad because I use purple for x. Maybe you don't care. I use h squared up here is equal to these things. So great, h squared is equal to that. Well, down here, h squared is also equal to these things. So I'm going to take these things and these things and set them equal. So maybe I'll use orange since I started with that. This thing equals this thing, and I'll just put them over here for now. So b squared minus, I'll keep my x color coding, x squared equals this stuff. So a squared minus c squared plus 2cx minus x squared. And I need my color coding. I've got x there, and I've got x here. Cool. The next thing that's nice is over here I have a minus x squared, and over here I also have a minus x squared. So those things can just cancel each other out. Just think about if you have balancing scales, we've got the same thing on both scales. You can just take it off both sides. So great, we're already simplifying this. Now I'm down to b squared equals a squared minus c squared plus 2c, and we still have this x guy that we don't like. We'd like to get rid of that x. So now I have to go back up to our original triangles and say, okay, what relationships do we have? I know x is here. I've used the Pythagorean theorem. In the law of sines, we use the sines here. So what other relationships do I know that I can use to get rid of x? And when you look at, for angle A here, well, in respect to angle A, x is adjacent, and b is hypotenuse. And I'm going to b because I wanted to get rid of h, and I don't have any h's left. Now I want to get rid of x. That's what I'm working towards. So, okay, we have adjacent and hypotenuse. Well, I could check my SOHCAHTOA, and I see adjacent and hypotenuse. I can already stop there. I can see its cosine. So now I can use this relationship. That relationship is cosine of A equals the adjacent over the hypotenuse, which is x over b. X over b. So I'll multiply the b to the other side, and I get x equals b times cosine A. Great, so now x is equal here, like this x is equal to these things, and so I'm going to put those things in here for this x. Yeah, I guess I'll do that before I go to the next page. I knew I'd run out of space, so I left myself an extra page here. That's b squared equals a squared minus c squared plus 2c times b cosine A. This will be kind of gross looking, but it'll work. If I just do this, then I won't have to write it again. Gross looking just because my handwriting's gross looking. paste. Okay, great. So we've got this equation now. This is the law of cosines. I guess I could go ahead and label it, but we can make it look a lot nicer. Law of cosines, which is the same as the cosine rule in the UK. Cool. We can make it look nicer though. And here's how we can make it look nicer. When I look here and I see we have the thing that's unique here, we have like side A, side B, side C, we've got sides all over. But the thing that's unique is we've got this angle A here. So because that angle A is there, it's kind of a clue to me that this function will look pretty if we solve for A squared. So I'm going to get A squared alone, which means I'm going to add C squared over here, and I'm going to subtract that stuff over to the other side. So I get my A squared is equal to B squared. I'm adding the C squared, so plus C squared, and then I'm subtracting this other thing, minus 2, and I'll just rearrange these to B, C, cosine A. Here's what we've learned about the law of cosines. So we've proven the relationship between the sides, like we have all three sides built in here, and one angle. So that means if we know two sides and an angle, then we can find the third side. If we know all three sides, we can find an angle. Like we get all kinds of relationships here, and they turn out to be different uses than the law of sines. So now we have this generalizable rule that we can use for any triangle. Like this only has A's, B's, and C's, and those A's, B's, and C's are the parts of this non-right triangle. So great, we can use that on everything. The last thing I want to say about this is that this is interchangeable. Oh no, I have two other things. This is interchangeable with also saying I could switch these out. The key is that if this is A, then this is A. And then the B's and C's are the other parts. So it's interchangeable. I could say B squared equals A squared plus C squared minus 2AC cosine B. Or I could say C squared, and then these things flip, so now I have A squared and B squared minus 2, and AB then go here. And this is cosine C because it matches the C over here. So these are all the law of cosines, and we could use any of them with any triangle, like not a right triangle, any triangle. These relationships are valid. So let's look at, before we look at examples, I'd like to point out, this is the Pythagorean theorem. So this really is the Pythagorean theorem. And then we have this extra constant that we have to use to adjust the Pythagorean theorem because it's not a 90-degree triangle. So 90-degree triangle is Pythagorean theorem. For any triangle, we just add this extra piece and it all works out. Let's look at some questions from your assignment today. Cool. So we've got this relationship. Let me go ahead. I'll type it up here. It says A squared equals B squared plus C squared minus 2BC cosine A. Cool. And we can interchange like A, B, and C basically. So cool. In this triangle, when I look at number one, we've got in ABC, B is 45. They've already marked it. AB is 10 centimeters, already marked. BC is 12 centimeters, already marked. Calculate the length of side AC. So this is the piece we want to find, and I'll just label it lowercase b because it's across from big B. And then I'll use this formula, but notice here we know angle B. So the form I'm going to use for that, since I know this has to be a cosine B, so up here I'm going to start with B squared, and it'll equal A squared plus C squared minus 2AC cosine B is the form of it that I'll use. So great. B squared, well, B is the thing I want to know. I don't know what that is yet. It equals A squared. Well, A is here. So that's 12 squared plus c squared. C is here, so that's 10 squared minus 2 times a, which is 12, times c, which is 10, times the cosine of b, which is 45. Great, we have this big expression. Well, let me just break out my trusty calculator. Some people, by the way, were having calculator troubles, and I would just direct you to use Desmos. Desmos is a great calculator. It's for free online. I guess I'll erase these things just so we can see a little better. And cool, I want 12 squared plus 10 squared minus, and we don't really need to, but I'll put parentheses here. Oh, actually we do need to. Parentheses 2 times 12 times 10 times, I'll put another parentheses to make sure, 45 cosine, and close that parentheses. So 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of 45, and it says that that's is that the whole thing? Yeah, it must be. 74.29 sounds unreasonable. Oh no, it's not unreasonable. 74 point, what was it? 74.3, and that's b squared. So I want to square root that. Can I bring this back? I can't. So 74 point, I'll just take more decimals, 29, because I want to make sure that I have enough precision to be correct to the third decimal place. 43725, that's plenty. Square root. I get 8.62. So B is 8.62. And since we square rooted this, we should acknowledge that there is a positive and a negative square root, but in our case, this is the physical side of a triangle. It cannot be negative. So this side is 8.62. Great. I don't think you'll have much troubles with the next ones. Like, go ahead and work through some. I do want to look at 5 because it's significantly different. So in 5, we've got triangle XYZ. XY is 15, it's marked. YZ is 13, marked. ZX is 8, it's marked. Calculate the size of angle X, angle Y, and angle Z. So what's different is now we know all 3 sides, but we don't know this angle, so we'll have to solve for that. So okay, let's start out with the first one. We want our angle here to be X, so I'm going to start with side X up here. So side X is 13, so I've got 13 squared, and it's because I want angle X, so I'm looking and starting at side X. 13 squared equals the other 2 sides, like side squared plus side squared, so that's 8 squared plus 15 squared minus 2 times 8 times 15, that's a minus, times the cosine, I know this is hard to read, sorry, of angle X. And the key is that's the piece we don't know. So let's simplify some of this. I'll go ahead and get out my calculator again. And in my calculator, let's simplify some things. Well, I know 13 squared is 169, but 225 plus 64, I just don't really want to think. Plus 64, 289, 289 minus 2 times 8 times 15. Well, 2 times 15 is 30. 30 times 8, well, whatever. Oh, it's 240, but 240. So this is 240 cosine X. So There was one time before, I forget which topic it was, but one time before the Lammas law came up. Kerry Lammas is a guy I used to work with, and he says the Lammas law is when you look at an equation and you see something weird, you always get the weird stuff alone. This thing is weird. So I'm going to subtract 289 to the other side, and then I'm going to divide by 240 next. So 169 minus 289, well, I closed my calculator. 169 minus 289 is negative 120, so I get negative 120 equals negative 240 cosine x. And then the weird stuff is here. So next I'm going to divide by 240. So negative 120 divided by 240 is negative 0.5. Wait, those should both be negative. My bad. Negative 240, positive 0.5, positive 0.5 equals cosine x. And sorry, I switched colors. I didn't mean to do that. Then last step, I want inverse cosine of that 0.5. So trig second cosine tells me that angle is 60 degrees. So I'll just say x equals inverse cosine of 0.5, which is 60 degrees. So x here is 60 degrees. Cool. And we will have more practice like this, but right now you already have more practice like this because you'll have to solve to get y and z also. You can tell these ones are a little bit involved. This is much more difficult than the sine rule. At least the equation itself is. But I think you have enough context now. If you have questions, like especially, there's like bearings here. We've talked about bearings only a little bit. If you have questions, I'm in Teams. So send me a message and let's jump into Teams and hook it up. Best of luck. Talk to you guys in a bit.